So this week we're extremely happy to have Wenqing Pham visiting us from Berkeley. So she got her PhD at Stony Brook doing direct photon studies at Phoenix. Since then, as a postdoc, she's moved on to ALICE, where she's really been a pioneer in jet substructure measurements. And in particular, she's distinguished herself for her exquisite taste in which observable she's study. And so today she'll be telling us about some of her work, both at ALICE and in the future electron ion collider. So take it away.
All right, thank you very much for the invitation and for the introduction. And yeah, today I'm gonna talk about this exquisite test, jet substructure with energy correlator that colliders, more specifically the Large Hadron Collider and the Future Electron Ion Collider. And this talk will mainly be like in three parts. First, I'm gonna do introduction / motivation, like why jet substructure and why energy correlators. And then the second part, I'm going to show the result of energy correlators and PP collisions from the Large Hadron Collider. And then the third part, I'm going to show some studies for the Future Electron Ion Collider using this observable. And as this year marks the 50 years anniversary of the QCD, so I'm going to do it like with a historic perspective. Starting, if it moves.
Click with your mouse.
Yes. Okay.
I
see. Okay, cool. So I'm gonna start with an experiment that to really discover that there are more fundamental particles inside the nucleon, which then led to the triumph of QCD. So the experiment is at the Stanford Linear Accelerator Center, SLAC. And at that time, SLAC is able to accelerate electrons to orders of 10 GeV. And then the experiment run is like they will then run that high energy, in quotation mark, electron beam to a fixed proton target. And then because the energy is as this regime that the electron and proton can actually interact in a very inelastic manner, and the virtual photon like mediated during this electron proton scattering reached high enough energy, like usually you can use Q square, the momentum transfer square, to characterize the scale of this virtual photon. And that's directly linked to like the spatial resolution that this virtual photon can probe inside the proton, basically how small distance structure can this photon see. And then what's discovered there is like one of the results is this reduced cross section for this EP scattering as function of Q square. And if you look at the data points, you see that this reduced cross section, which encapsulates the proton structure, actually doesn't have a strong Q square dependence. And the only explanation for that is there is point structure inside proton, and then you're hitting this virtual photon is hitting that point-like structure. And this constituent particles later than this referred to actually understood as valence quark together like with the discovery of Jade's side and other theoretical development. So now we understand that there are actually more fundamental particles inside nucleon. There are quarks and gluons, and the underlying theory for that is quantum chromodynamics. So from late 1960s, with this orders of 10 GeV electron beam, we're able to see that there are finer structure inside the proton. Moving on with time, 10 years later, people are able to collide electron and positron at even higher energy at about 30 GeV. And with this experiment, we're actually able to directly observe the debris of outgoing quark and gluon. And the collider for that is the Petra, and it's at DESY. And I'm showing one like event for like the process taking place at this collider, and that is E plus E minus annihilation into a QQ bar pair. And you can also have one of the quark Armstrong gluon. And for this process, like here is what people observed in the experiment, taking tussle as example. So this three like collimated spray of particles actually are coming from these three prongs in this Feynman diagram. So then really like at this time, people are able to directly see this like quark and gluon jets. And this also marks the discovery of gluon. And that's actually our topic of today. So these partons, they separate like impeded and then develop their own like private multi-hadron image. And this multi-hadron image are jets. And moving on, like 30 years later, we now have the Large Hadron Collider at CERN. And you can see like here I show a bird wheel. This is no longer working, but that's okay. So here I show a bird wheel of like Petra. Actually, you can also see like Hera right here compared to the LHC. You can see the diameter is very different. And the energy, like the center of mass energy now goes from 30 GeV to 10,000 GeV. Oh, thank you. Let's see this. Okay, cool. And that really is like there are tremendous work from many engineers and physicists that made it possible. And you can see from this chart that the center of mass energy, how it grows with years, and from Petra time era to LHC era, it really increased by 2 orders of magnitude. So now we're at the energy frontier, and not only we're at the energy frontier, we're also at the luminosity frontier. And this energy and the luminosity frontier, what it gives us is a lot of QCD jet to be studied. And not only we have this new generation of accelerators, we also have a new generation of detectors, faster and more precise detectors, which together allow us to really study the abundant jet produced at LHC with high precision in a wide kinematic range. And the reason I kind of want to emphasize that there are a lot of like QCD like talk this year. Mostly I heard this from theorists, and I want to emphasize that the discovery really like how QCD achieved like the stage today. It's also largely related to the development of the instrumentation, accelerators, and detectors. And now here I want to show you this beautiful event display from CMS, which shows like a multi-jet event. And really we set to show that now at LHC, we have a jet factory. And this jet factory really like offers an ideal laboratory for QCD and also beyond standard model physics studies. So yesterday's discovery now become today's precision physics. And when you can study things with enough precision, maybe that can lead to tomorrow's discovery. And today we're gonna focus on the QCD part. All right, so like in slide 2, I mentioned that like the way we observe the outgoing quark and gluon is like we observe them as a collimated spray of hadrons, and how that happened. And that's actually like related to a fundamental property of QCD, which is confinement. And I want to show that using like the lifetime of like what really happens to a parton in vacuum from the time it is produced to the time it is observed. So the process taking place at the beginning, like taking the PT collision as example, is you have a 2 parton interaction, like from each beam, and they produced a parton going out, shown by these 2 arrows. And then what happens is that this parton will actually radiate gluons, and that gluon can also branch out to QQ bar pair. And then it goes to a cascade of like lower energy parton production. And that usually is referred as parton shower. And this usually happens at a lower energy scale. So the whole process can happen at TeV, 100 GeV, and this parton shower will then bring this very hard initial parton to a lower energy scale. And there's also like an angular ordering feature in this QCD radiation that the earlier radiation at higher energy regime tend to have a larger opening angle in this split. And we'll come to that feature with energy correlator later. And then when they reach to a certain energy scale, confinement will kick in. And that's when this like QCD color charged particles will actually neutralize this color and form this like more stable hadrons and color neutral hadrons at lower energy. And even as for today, the mechanism for like how confinement take place is still unclear. And that remains like a very important question for us to answer. And experimentally, really how we define jet is basically random jet clustering algorithm, which can cleverly define, like identify what particles come from this Hall process. And those are our jet. And really like, if when we look at jet, there are, I would say, two facets to it. One is to treat it as a proxy for the originally produced high energy quark gluon. And that is in a very high energy regime, which correspond to a smaller, strong coupling constant. And in which regime, like you can actually use perturbative techniques in QCD to do a lot of calculation, and those measurements can be used to constrain alpha S also. But there are more actually one can do with jet, which is the jet is a multi-hadron object. If we look at how those particles are distributed inside jet, look inside the radiation pattern, that can actually open us the phase space, and we can then like not only study the perturbative regime, but also towards a non-perturbative regime, and which includes a confinement phenomenon. And that is jet substructure and why we're interested in it. Here I want to start with a few jet substructure observable examples, like what can one actually look inside jet. For example, you can look at the single particles inside jet. You can look at like each particle, how much energy it carries from the jet. That's a fragmentation function. Or you can look at all particles inside the jet, and then like, you make a function that it depends on the momentum of like each particle. Here, the example is angularity. And you can see the two term, one term is the longitudinal energy fraction it carries. And then also like transversely how it distributes itself inside the jet. And you can even like tune the parameter to get different sensitivity to the longitudinal part and transverse part of the fragmentation. Or you can look at the subset of particles, for example, the Groom jet, the jet that has a part that the jet that the white and soft radiation inside it already groomed away. So you're only looking at the, say, the perturbative core of this jet, so that like more calculation can actually be made, so you can learn something about the PQCD. And today, we're going to focus on the correlations. So we're going to look at the correlation of particles inside jet, or say the correlation of energy flow inside the jet. And the rest of the talk will be divided into two parts. First, I'm going to show the result of the, and then I'm going to show some studies for future electron divider. And the questions like I want to pose before I even start showing any result is like, for the PP part, what can we learn about the perturbative interaction of program gluon? And then what can we learn about the non-perturbative aspect, for example, hadronization? And for the second part is like, if we can understand like what happened in the vacuum, can we then use that as a tool to understand like how the medium modifies the jet evolution and something about the medium? Okay, so first part, I'm gonna start with the introduction on the energy correlator. What are they? And this is actually not a brand new observable. It has been like first proposed and then measured at the Fuzzy minus Collider quite some time ago. And back then, this energy correlator is measured as an event-shaped observable. More specifically, what's done is you look at a particle produced in the E plus C minus event, and then like you make pairs, you find like how many pairs are there. And every time you find a pair, like you weight the you weight that count with the energy weight, and that's calculated using the product of the energy carried by each particle divided by the total energy, like from the beam, which represent a Hertz scale. And then you get its energy weight, and then you look at like how many pairs I have from 0 to 180 degree, and then you look at the cross section, what is its dependence on this pair distance. So it's been measured as E+, E minus experiment, and actually it's also calculable. It's an infrared collinear safe observable, and actually it can also be calculated to high accuracy, and then time is used to constrain alpha S. Actually plays a very like powerful constraint on alpha S. And what I'm going to talk about today is to actually look at kind of, I can go back, focus on this collinear limit. Like say, I'm not going to look at like the whole event. I just am interested in jet. So looking at this collinear limit, how the energy correlators look like and what can that teach us. And so the way it is defined here, it's pretty similar to the event shape definition, just that for the event shape observable, like they look at the whole event, here we treat jet as our event. So the experiment then start with the jet clustering, and once you have the jet, what it will do is then you will make pairs of the jet constituents, and then you count how many energy weighted pairs are there as function of pair distance, which is calculated using the quadrature sum of the delta phi and delta eta of these pairs. And the energy weight in this case is calculated using the PT product of the particles inside the pair, and the normalized by this like a Hertz scale given by jet PT squared. Today I'm gonna mainly focus on the 2-point energy correlator, and I will really refer that as EC. But one can also measure it to higher point. One can look at the triplets, the triangles, or like even like 4 particle correlations inside the jet. Taking the 3-point correlator as example, one way you can measure it is to measure the full shape dependence, like how many equilateral triangles I have, like how many like triangles of other configurations I have. Or another way is you can project these triangles to its longest distance side, and then here to measure this projected 3-point correlator, later referred as E3C, is then you just like count the number of weight triplets as function of this longest distance. And the energy weight here in this case is still the PT product, but now you have 3 particles, and then for the energy weight, you have PT jet to the 3rd power. So why energy correlators? Why this 2-point energy correlators? So one advantage is a well-defined probe, which already is shown like in the E+, E minus experiment, that it's IRC safe, and the PQCD calculation is available already. And it's even made available for just looking at charged particles inside jet, where one can use the tracking system to make precision measurement. And then another advantage is because we have this energy weight here, so some soft contributions that is not coming from the process we're really interested in, for example, multi-particle interaction or the underlying soft interactions, will be suppressed by this energy weight. And hence, like, we do not need to like do any trimming or grooming on the jet before comparing to the PQCD calculation. And another big advantage comes from like the fact that we're measuring this energy correlated cross section as function of the opening angle of the pairs. And what this opening angle RL gives us is like one will be probing a big scale with a fixed opening angle. And now I want to come back to like this parton shower part. Like in the previous slide, I mentioned that while this initial like energetic parton goes through this parton shower, it will radiate gluons, and then the gluon can also branch out to PQ bar. And during this radiation, there's actually angular ordering behind it. And it's in the way that the early and more energetic splitting take place. The splitting from the early and more energetic splitting will tend to have a larger opening angle. And that's the opening angle we're measuring here. So this RL, if you're looking at large RL, that will be correspond to the high virtuality or say high energy splitting, early splitting, and the low RL will more correspond to the low virtuality and later splitting. And then by marrying this energy correlator at large and then small angle, we'll be able to really like sweep from the perturbative to non-perturbative scale. And also, like we know that the confinement at some point need to kick in. And then like with this EEC, then somewhere in between the large and small angle, when the virtuality or say the energy scale approach like over lambda QCD or somewhere around there, the energy correlators should undergo a transition, and we should see like a signature for that. And if it really like happens in the way that when virtuality approach certain energy scale, then we know that virtuality is proportional to the jet PT times RL, then the transition region should have a dependence on the jet PT in the way that for more energetic jets, we expect to see the transition at a smaller angle. And now what we want to do is to see how it really looks like in data. And this measurement actually has already been carried out by several experiments, the CMS and the STAR. But today I'm going to mainly show the result with the ALICE experiment and a very quick intro on the ALICE detector. So here this ALICE detector, and you have like tracking system, and then you have the PID partly provided by also the tracking system, time projection chamber, and the time of flight, and then outside you have some colorimeter coverage. And what we mainly use for the analysis is the tracking system. We're gonna look at the charged jet and charged particles inside the jet. And ALICE features a very high resolution tracking system composed of the inner tracking silicon system and the time projection chamber. And together, like we can measure the momentum of charged particles, high precision, and of course, the measurement need to be correct for the detector effects. And because previously I mentioned that this transition for the confinement should have a jet PT dependence, because we also want to make the measurement in different jet PT ranges. And that's what we did. So the measurements carried out for the R equal to 0.4 charged particle jets in this jet PT range from 20 to 80 GeV in 3 jet PT intervals. And the result now is shown on the right-hand side. The y-axis is the cross-section normalized by the number of jets, what's the inclusive jet production. The x-axis is this opening angle, and the 3 PT result is shown by blue, green, and red, going from lower to higher jet PT. And what we see here is that there is different RL dependence at the small angle region and large angle region. And that really is consistent with like a perturbative scaling behavior and something very deeply non-perturbative happening at the small and large angle. And also somewhere in between, we see this turnover behavior. And this turnover behavior also shows a jet PT dependence in the way that it shifts to smaller angle for higher jet PT. And that is where we expect confinement. A closer look at like really this different scaling behavior at different angles. So first, let's focus on the large angle region, like where this should be the perturbative region, and let's treat the PQCD calculation next to it. So black is the data point. A PQCD calculation is orange line, and you see this like a very nice agreement between the PQCD and data, really confirming that like this side is the PQCD scaling behavior. This RL dependence is governed by the perturbative evolution. And here we're looking at the Platonic degree of freedom. And now if we go to the other side, what we see is this cross-section actually increase as a function of RL. So that's completely different RL dependence. And this purple line right now, like going through the data very nicely at small angle, it's actually just a linear line. And that's something one would expect if it's just like a uniform distribution of particles or it's a uniform distribution of energies. There's like no correlations. And that will give this linear line that describe the data pretty well, which indicates that for this small angle, like we're just seeing like a bunch of like free hadrons and the integral freedom is the height. And then in between, like this transition would naturally like lead us to think that it would be the hadronization. And here is just like showing the comparison for other like JET-PT ranges of full gallery, the 2040 GeV, 4060 GeV, and 6080 GeV, and the message is the same. At the large angle region, you see the PQCD scaling, and then like it undergoes this transition, and then it deviates from the PQCD because the non-perturbative effects start to dominate. And then there is a transition for the hadronization, and then it goes back to this free hadron scaling. And just like one more way we can look at this like separation or like even confirm like this PQCD scaling, separation of PQCD scaling and free hadron scaling is to look at the ratio also. So for the perturbative large angle region, because it's governed by PQCD, the 3-point and 2-point correlators, they will have slightly different dependence on RL. And that difference actually reflects alpha S. Or for the small angle region, because there's no correlation, one expects a pretty trivial linear dependence from both 2-point or even higher point. And that's nicely shown by this E3C to EC ratio here. And for the large angle, you see this rise as a function of RL, and there are like theoretical work showing that the slope actually is directly proportional to alpha S at leading order. Well, for the small angle, this free hadron region, the linear scaling cancel each other, and you just see this flat trend here, which again confirms that like at a large angle, it's PQCD governed, while small angle is just non-interactive. This measurement has also been done by CMS experiment for several JET-PT, for a wide range of JET-PT. And they also like show the slope, how the slope actually changes as function of JET-PT. And I find this result very impressive because like we take this slope at alpha S, you can see how this alpha S nicely decreases towards higher energy scale. And this is a direct observation or representation for the running of the strong coupling. And then they're also able to extract the alpha S at the ZMOS. And this actually is a very precise extraction from jet substructure. And for more details, you can check Anania's poster at Dark Matter, and for more details on the CMS measurement, you can check Chengfeng's talk. And now, like we've seen that there's a large angle region, nicely follows PQCD scaling, small angle is free hadron scaling. And now let's take a closer look at the transition region in between. So from this plot I've shown before, like the EEC cross-section function of RL, this transition region shift to lower angle towards for jet with higher PT. And that's expected because they're thinking that when the virtuality approach certain energy scale, this transition takes place. So what if now we just look at how this cross-section depends on the virtuality, so the energy. And to do that, then like we change the x-axis from RL to PT times RL, and to focus just on the shape or say the dependence, then we normalize the magnitude of distribution from different jet PT to the same magnitude. And then what we see at the end is like quite strikingly, all this different distribution from different jet PT now collapsing into one common trend. And that really like this trend is sitting at 2.4 GeV with like no more like jet peak dependence, indicating like a universal like transition energy scale or like hydrogenization energy scale at this position. And we also compare this data to state-of-art models with the Platon shower and a different hydrogenization mechanism. More specifically shown here is Pythia and Hurwig. So Pythia has a long strain breaking hydrogenization implemented, and Hurwig has a clustering hydrogenization implemented. And the idea of comparing data to these two models is then like to answer like if this data can offer us insight on discriminating what is really the dynamics for the hydrogenization. Is it strain or clustering? So the data is still shown by the black data points, and the Pythia is in red, Hurwig is in blue, and the three different plots correspond to three different PT range. And qualitatively, just by eye, you can see they actually all describe data reasonably well. And for a closer look, then it's shown the bottom ratio plot. And then like with the ratio, you can see more clearly, there are actually some differences between data and this two Monte Carlo model. And one thing we observe is that as for this peak transition position, Hurwig actually described data slightly better than Pythia. And Hurwig's transition position is sitting, if you look at the blue, it's sitting at a slightly lower angle compared to Pythia. And that's consistent with a later hydrogenization with clustering. But given the current magnitude of difference and certainty on the data, and also like having in mind that there are more differences between Pythia and Hurwig, other than just different hydrogenization model, I would say this data has really big significance in really telling what is the underlying hydrogenization model. But going to a higher point, for example, looking at the 3-point, and making more differential measurement, for example, looking at the like-sign, unlike-sign pair, or like meson-meson pair, meson-baryon pair, can potentially offer more insights into like what really is the underlying hydrogenization mechanism. And now moving on to the third part, or say the second part of the result I want to show today is then we have seen that this EEC can be used nicely in the proton-proton collisions and to help us understanding the PQCD and hydrogenization. What can we learn more from it? For example, at the future electron-ion collider with the EP and EA collisions, what can we learn about the medium? And also like, will we still see the hydrogenization scale in EP will be that at the same place? And how the interactions between the jet and the nuclear medium modifies this energy correlator, and would that actually imprint some scale of this nucleus? And the electron-ion collider coming up is the ideal facility to answer this question and explore more. And here I take a quote from the EIC white paper showing that understanding the interaction between this outgoing struck proton and the nucleus and at what scale it hydrogenizes also is one of the important questions you want to answer. And moving on, just a very quick general introduction on EIC and the detector we're going to use or being built is, so EIC is a very versatile and a high luminosity facility. The energy can vary from 20 to 100 GeV, and that offers a wide kinematic coverage for this DIS process. And also like very nicely, it has different variety of ions, ET collisions, E-carbon collisions, all the way up to potentially E-uranium. And the luminosity is also at the frontier, so we can collect enough statistics. And then here, like on the top left, top right, I show you like a table of different nucleus species at different energy. And here is a bird view of the EIC, which will be viewed at the Brookhaven National Lab. And right now, like we're also very active, like work on like making the detector design ready for the project detector, and that is an EPIC detector. And this detector features a very hermetic coverage on marrying like the produced particles that have the high precision tracking and vertexing system highlighted here to measure the momentum of particles, and if they're produced from the primary collision, or like if they're from flavor decay, which then will have an off-vertex production point. And also like there's also full coverage of particle identification system, EM-Cal, and hydraulic colorimeter to capture to measure photons, electrons, and neutral hadrons. And here is a timeline for EICU right now. We're around here. So the project detector design is mature and preparation for CD2 and 3, which basically will mark the start of the construction and some procurement. But also from this chart, we can see that data is not there yet. So the result I'm going to show is not from actual data analysis, but to analyze the event produced from a realistic event generator for the EP and EA collisions. So what we use is called eHygiene, and that's specifically developed to study the nuclear modified jet evolution in the events. And for the EP collisions, it's equivalent to PCR. And what happens there is basically, I have mentioned in the first slide, that you have an electron exchange virtual photon with a quark inside the proton. And then the struck quark will go out and then shower into a stream of particles, which is jet. And then for the EA system, then what is implemented in addition, and that's what we're interested in looking at, is they have the medium modified particle shower. The PT Browning, and also their PT Browning with multiple collisions, and also there's medium induced parton splitting. And also, like, this is not just like some random event generator. It's also benchmarked to the previous measurement from the Hermes experiment. And for more details, you can check this reference here. And before I show any plot, one other thing I want to mention is about this energy wave power. For the previous result in proton-proton collisions, like we have used like n equal to 1. And because in PP collisions, we have this multiple interaction and the line event, and we want to suppress that with this energy weight. So, and it's a good choice, and then usually it's a default choice. But for the electron ion collider, actually, we don't have to worry so much about this background. It's a cleaner environment, and so we're actually able to use different energy power. We did a study systematically varying the energy power, and we found out that decreasing this energy power, we get more sensitivity to the soft signals, like from the modification on the jet from the medium. And that's what we're gonna go with. So for this cleaner environment in EIC, for the rest of the result, the N used for this energy power is 0.5. And also because of this environment is cleaner, we can even do larger jet radius, and the jet radius used for all the following results is R equal to 1. So let's first look at the vacuum baseline. So this is a result from EP. Sorry, the axis is missing. So the y-axis is this EEC cross-section. X-axis is the opening angle here. It's denoted as theta, but it's really just equivalent to the RL that we looked at before. And what we see here, like with n equal to 0.5, we also see this nice transition between this PQCD scaling and the free hadron scaling. So that's also there in EP collision. And then how things look like in electron nucleus collision. And that now is added to the next to the EP curve shown by this more colorful curves. And immediately what we see is there is a modification of the distribution as a large angle region. And the difference between these colorful curves is different transport coefficient, which kind of correspond to how strong the rate of interaction between jet and the pronucleus medium. So the modification takes place in the large angle region. And if now we recall that the splitting angle is related to the splitting time, then it all makes sense, because then the large angles are usually the early splitting, which take place inside the nucleus. And hence we see mainly the multiplication at the large angle. And the tuning this transport coefficient Q hat, like from orange to magenta, it's increasing this K parameter, which is related to Q hat, like increasing K, it's increasing Q hat. You can see that we also see more modification with a larger Q hat. And we see this modification at a large angle. Now I want to talk a little more about the onset of the modification. So I mentioned that the modification takes place at the large angle, which makes sense because the large angle is early splitting, which takes place inside the nucleus. If we follow that line and then follow this relationship between the splitting time and the opening angle, from large splitting, which takes place at early time, to late splitting, which takes place at later time outside the nucleus, there will be a critical time when your splitting happens just at the boundary of the nucleus. And you can calculate this critical time. That will be just at the order of nucleus size. And then you can calculate what will be the onset angle. And this is the result. And that's a very easy calculation. You just relate this to the path length versus nucleus size L. And you will get that this onset angle will be related to 1/√√ jet PT times the path length. So there is a jet PT dependence. For larger jet PT, this angle should move to smaller angle. And there will be a path length dependence. For larger path length, this onset will also move to smaller angle. And in the next two slides, I want to show them, like, if really we observe this scaling, or say this PT dependence and nucleus size dependence, starting from the PT dependence. So one way to see this PT dependence is because this onset angle has this PT dependence, then we can actually factor out this PT by placing that into this x-axis and then comparing different jet PT. If this scaling behavior really holds, then the onset should take place at the same place. And that's what we see here. So here on the y-axis, now we're only focusing on the relative difference between E gold and EP. And we see that for different jet PT results from 5 to 10 to 20 to 30. Now they all rise up nicely at a similar location. And now to the different nucleus size dependence, and the EIC really, I would say, it's an ideal facility to test that because of the variety of the beam it can provide us. And we checked all different electron nucleus conditions from helium to carbon, calcium, all the way up to uranium. And then like from this blue to red, you're moving to larger and larger nucleus size. And what you can see is that, like, when looking at this EEC multiplication as function of theta times square root PT, it moved to like a slightly smaller angle, this onset for larger nucleus. And we can use the same trick again to view this nucleus size dependence, like we can put then the nucleus size dependence into the x-axis to factor that out. And then the expectation is that then they should onset at a similar position, and that's I think here like they're onsetting at a similar position compared to this one. So as for the magnitude of the modification and really the exact shape of the modification, that we think like will be sensitive to the model details, and it will be exciting to see more development on this, especially in the analytic calculation, to show really like how the modification would look like. And that can provide sensitivity, say, on constraining Q hat in the conucleus. And what's even more exciting, I think, for me, from the high-ion side, that not only we can study the cold nuclear medium, we can also study the super hot nuclear medium, namely quark-gluon plasma produced at the relativistic hyper-ion collision, and they will have a medium of deconfined, strong coupled quarks and gluon, and how that modifies this energy correlators inside the jet. Will that modify the hadronization? How that will modify the perturbative splitting? I think we can potentially learn a lot, and there are already a lot of studies on that and data analysis ongoing. And here, one of the studies done is actually one of the studies like shown done by the theorists is that from different theory models, like they expect different expectation, different multiplication at large angle, and the underlying picture is similar to what we have seen with the EA collision, that the multiplication at large angle correspond to the Earth splitting inside the QGP. And although different models gave different multiplication, but you can see that it onset the same place, and that should be sensitive to the medium size. So with that, I come to my conclusion. So energy correlators can prove dynamics or the evolution of jets at different scales. And there's nice separation of the perturbative region, the hadronization region. And we can see that the hadronization transition is at a fixed place, function of PT times RL, which is around 2.4 GeV. And higher order and more differential measurement can shed more light, I think, on the hadronization dynamics. And I think some people here are already working on it. And the future electron-ion collider, I think this observable can be used to also study the interaction between the jet and the cold nuclear medium. I can actually offer like phantometer resolution for the nucleus size. And I think there are more to be explored. And most excitingly, like EIC is still some time away, but we do have the high-ion data already. So it'll be very interesting to see that how it look like when it's inside the QGP. And there are a lot of ongoing work on both theory side, experimental side. So stay tuned for more interesting studies. Thank you.
Thank you very much for that beautiful talk. So are there any questions? You got your hand up.
Could you go to slide 28?
Sure.
Great talk, by the way. So I was just a little confused here. On the left plot, I think you said that the onset is at a different position for each of the different nucleus sizes.
Right.
But it seems to me like they're all kind of happening at one.
Yeah, here it's a kind of a little bit difficult to tell, I would say, with this part, but the trend I'm mentioning is if you look at this red and then this blue, so this blue actually fluctuate down. So you can see that this blue, which corresponds to the helium, actually onset at a slightly smaller angle. And yeah. Right, but there are a few outliers that we do also observe.
Okay, because then when you normalize by the nuclear size, there we've expected to have an onset in the same.
Yeah, more similar position.
But there it does look like I can see separation between helium and the uranium.
Yeah, there are a few that I think align better with each other, and I think here I want to say that if you compare this ball to this ball, like, this rising trend really look more consistent for different nucleus when we use the scaling. But indeed, there are also variations. So I would say, like, right now, it looks like this A to the 1/6, like, seem to align them better than like no A dependence. But it would be also interesting to further explore, say, other like models or like analytic calculation, or potentially with data in the future, like really what is A.
There could be maybe other effects besides just the nuclear side as well, right? Thanks.
So we'll go the same. Can you go back 1 or 2 slides? Yes. So is there a reason why you picked specifically n equals 0.5?
Like,
Yes.
is it just that there's not much background expected in the EIC, but
Mhm.
even in the EA collisions?
Right. So we did study like how this modification looks like for different men. Maybe I can go to that all. Yeah, so here is like looking at how here's looking at how the modification, like as function of C, that will change for different energy power.
Yeah.
And the n equal to 0.5 corresponds to red one, which gives the largest signal. And that's one of the reasons we're choosing it. And because like here, the background won't contribute so much. So we can actually choose that and still be looking at a clean signal.
So now I'm wondering about this because when I think about increasing N specifically in just PP, like you should be like suppressing the background. But if there's not much background, then why is this suppressing it cause that dip now?
You mean why there's a dip with n equal to 1 shown by this green?
Yes.
So this dip we think is actually coming from, you know, how the modified splitting.
Yeah.
How the splitting are modified and you know, the modification, what's detail of this modification inside the E hydrogen. So this dip, I think actually is part of the modification.
So if it's part of the modification, then for n equals 1, modification comes in at an later time than your.
No, I wouldn't say they come at a later time. So the modification, so I think no matter is like, you know, suppression or enhancement, their modification here, and it's flat here. So the onset actually is the same, which actually also should be the same when you vary just the energy power. It's just like when you have different energy power, then you have like, you know, different weight on the modification that carries different energy. And then with different energy powers, then you're kind of seeing different moment per se.
Yeah.
That modification.
But sorry, so if the onset for the 0.5 looks like it's like 3 bins to the right of the onset for n equals 1, if we're saying the dip is also modification.
So here is no modification, right?
Yeah.
And here like modifications. Oh, you're saying
compared the 0.5 doesn't look modified.
Right. I think for the green, purple, and blue, it's kind of very visible that they start from here. And the question now is the red, that they start from here or start from
Can you go back? So where did you say modification started for the 0.5, which bin?
So we didn't really quantify exactly the angle, rather we explored the PT dependence and nucleoside dependence. Yes.
I guess it could tell you that the hard versus soft modification
Right.
is at different places, maybe.
Yeah.
Right. And I think we can definitely check more, but to me, like, you know, there is actually modification, and that is kind of shown when using different energy power.
Okay.
It just kind of so happens that when you use this power here, the modification is pretty small.
Yeah.
That is consistent with 1. And maybe actually the one thing I can look into later, like really to quantify this modification angle here, it's probably better to actually look at different energy weight and use the one that has the most significant change around the onset angle to quantify that.
Next question was sorry, and then you next.
Yeah, sorry. So yeah, this is actually kind of related to this call and the one that Isaac's talking about. So can you you said like this K factor K parameter is like around you chose 4 for most of it, and is that like the interaction strength between like the nucleus? So can you elaborate more on this and why like specifically you chose 4?
Yeah, so that exactly is like kind of dictates like the interaction strengths like between the jet or like this parton, organic parton, and the nucleus. And there's also a similar thing defined for heavy ions. So using that, you also can connect the cold medium and hot medium. The main difference being hot medium has a much stronger interaction strands, and their Q hat is much bigger. And the reason why K is like set to 4 in default is because like when the eHygiene developers like benchmark their like result, like, you know, from the simulation to the actual measurement, K equal to 4 and the Q hat corresponding to that gave the best agreement.
So like in peak collision, basically this factor doesn't matter, right? So
Right. Yeah, exactly.
Thanks, Anand.
Yeah. So kind of going off of Andrew's question about the n equals 0.5. So I guess I was just thinking that like when you change this power to like, I think basically anything apart from 1, you lose IRC safety.
That's right.
So this is maybe more a question to Ian then, you must have thought about this. So I was just wondering, like, so in that case, like, what is so?
Like, can one still do comparison?
Yeah.
Learn from
And
that.
like, is there something else that the measurement needs to provide for the theoretical calculation to be like comparable?
Right. So maybe I offer my comment first and you can add. So that's actually a very good point. I didn't emphasize that before. Actually, it's only IRC safe for n equal to 1, but it is calculable, what I heard, for other n2, because there is this track function from the experimental data, and you just need to like get a different to me sounds like coefficient from that track function for different n. So it's still calculable, although no longer IRC safe. So you need this additional like track function input to calculate for.
And like that track function you would do like basically on the same data set and like the same. I like, is that something universal that you can pull out, or?
Yeah, that sounds like fragmentation function, which describe like, you know, how much the energy is carried by the certain final state particle carried from the initial particle. Should be universal, at least in the when the factorization can be applied.
Great. Any more questions for Wenqing?
I am new in the field, so it could be a very good question. But in the slide, I think when you show the difference, the comparison between simulations. So
Yes. This one?
yeah, so what could be the reason of one kind of simulation be better than the other one, and how much impact is to the
So usually like kind of, I think, at least for me, the general motivation, like when comparing data to the different models, is like usually different model can have different underlying mechanism for certain physics process, which we're not sure about yet. And then you want to see like the data compared to which model that has certain, you know, like physics process, like compares better. And then you say the data actually favors that mechanism. And then you learn more about the underlying.
But each of the simulations packages or so forth, it's using the same physics, right? So
not for a good part, but then for the homogenization part, it actually is using a different mechanism. That Pythia is using this long string breaking. There is color string, like at the end of the Parton shower, and they form this color string, and the color string break up to like a QQ bar and then form mesons and baryons. So that is the homogenization mechanism in Pythia, while in Herwig is a different one, that they just force all the gluon to go to that quark anti-quark. And then they do like first like a cluster, and then they have some like high energy scale clusters, and then like them decay. Short answer is it's actually a different homogenization mechanism. And we're not yet sure really like which one is the correct one, or maybe none of them are really the correct one. And they want to use data to see if we can tell them apart.
okay.
Yeah.
So just building off that point, should we expect the same behavior in quark and gluon regions, given that it's only the hybridization part that they do differently? Or is it like normalization affecting everything altogether? So we still can't just like compare Cork and Gluon. Like, I mean, Cork and Gluon as in large RL values.
You mean if I do Cork jet and the Gluon?
No, like when you do like the 3 regions, like hadron regions and then transition and
this is a Patang, or say the P2CP region. So you're asking why they differs in the whole region, like the Pythia and the Hurwig.
Right, like especially the large RL. Like, should I naively be expecting them to agree because they have like roughly very similar parton shower mechanism, or should I expect them to be affected because you normalize the whole thing together, including the hydronization effects that are implemented differently in the 2 different models?
That's actually a very good point. So I would say normalization definitely play a role, but even looking at the shape, I would say like they're slightly different, like in.
I guess they are, but do you know but why? I guess
Yes.
that's more the actual question.
Right. And then I would say, ideally, like I would want this 2 model to have exact same initial interaction and parton splitting. But the parton splitting part, actually, I think are also implemented differently in Pythia and Hurwig. So I think that may be related to why also have different shape in the large angle region. And another piece is that although the non-perturbative effect is small in the large angle region, hadronization do also can, change the scaling behavior a little bit. And I think theorists are right now looking at the power fraction that should be applied to account for the hadronization effect at large angle. So then the different hadronization from different model, I think actually also play a role here, although I would say less significantly compared to probably maybe the different shower inside each model.
They have different ordering, don't they? One is angular ordered and one is PTO. That should have effect.
Right.
In the parton shape.
And Pythia, I think, don't have next to leading order or like.
But Hurwig doesn't.
I thought that was the same between them.
Yeah, but okay. Okay.
I think that's a good point, and should think more like why they're different like in the whole region. Yeah, normalization does play a role, but there's also different shape.
Do we even know the difference of they have the same number of quarks and gluons? I think not. I think if you look at what the quark fraction of a 40 to 60 GeV jet is, they're different on the scale of the few percent you'll see.
Probably.
Which there is a different shape to the EDC for those 2.
Yeah, and also depends on like when they stop the parton shower in each model, and then that will lead to like different number of partons, right before the hadronization. Although I think at the end, like the total number of particles inside jet, that should be similar between the 2 models because they're tuned also to other observables merit.
Well, I guess like just to brainstorm a little bit, I guess like if you could turn off hadronization in both the models, it would be interesting to see like
there's gonna get
right.
each other, right?
Yeah, so indeed, like we have looked at just like at parton level, like how the distribution look like in Pythia, and like once we figure out how to do that in Hurwig, and we also plan to good luck. Right now, we are also like comparing to Sherpa, and I think Sherpa one can also do similar thing. And the one nice thing about Sherpa, at least what they advertise, is like really everything else are the same. The hadronization are different. Then one can check if in Sherpa, like it's the same at the perturbative region and pick up.
And I think our group in general also would like to know how to identify quarks and gluons in Hurwig.
So don't you talk? Yeah.
It's, yeah.
So I think some of these are becoming a little more specific, one-on-one questions. So maybe we can continue them in the afternoon. So I should just say Wenqing's around for the rest of the day and tomorrow if you'd like to chat with her. And there'll be a dinner tonight. And if you want to come, let Laura or I know. So let's thank Wenqing again for the great talk.